Welcome back. Let's continue our topic of three-dimensional space. We're going to talk about vectors today. I don't know if you've seen vectors in 2 dimension or not, but the same continuation will be holding on in 3 dimensions. So we're going to talk about it in general format. So let's say if you have 2 points in space, where A is our initial point, and B is the terminal point, then the segment, the line segment that connects the 2 points with the direction from A to B is what we look at as vector AB. So vector V is written as AB. Normally you might see arrows above or not unless they mention it. If they write AB, normally you will see this arrow above just to say the direction is from A to B, and they say V equals AB. But sometimes I will put the vectors there just to make sure that you notice this is not a point, it's just a vector. So the vector AB starts from A, ends up at B. The vector is basically a line segment connecting those two. The question is, how do we add 2 vectors? So let's say if you have 2 vectors, means you have vector U and V, how do you add? So you have vector U starts from A to B, for example. This is vector U. Vector V does not need to start from B. It could start from C and go to D. Let's say this is from A to B and C to D. But what you can do is when you add 2 vectors, that means you can assume that B and C are the same point and continue till you reach the point D. Where C and CD here is just moved up to here. So you kind of draw the parallel vector from the B to see where it ends up. Okay, so the vector V, which is in this case the point starting from C and ending out D, is basically the summation of these 2 vectors is basically adding these 2 vectors along the same parallel format. So if CD is in this direction, you draw this parallel to V, exactly starting from the point B. Okay, so what do you get if you start from A, go to B, then go to D? This is not exactly D, this is the point parallel to D. Where you end up with is this vector that connects the point A to the parallel, let's call it D prime or C prime or something like that, to end point of D prime. So this is the sum of these 2 vectors. Okay, so if you have 2 vectors, the triangle law says just draw those 2 vectors parallel. This is parallel to U, this is parallel to B, exactly the same length. So connecting those 2, this would be U plus V. If you add them together, if you start from here, go there, then go there, what you end up is basically starting from this point, ending up at that terminal point. I should have ignored the names and say from initial to terminal, initial to terminal. This would be your initial to terminal state, then you start from this initial to terminal state continuation. So you go from I to here, to the terminal state. Then from the initial of V, you go to the terminal state. Where you end up is basically the result of this summation, sum of 2 vectors. So graphically, we should know that our result is U plus V, which is connecting the initial of U to the terminal of V. How about if you have multiplication of a constant? This C is a constant, it's not a vector. It's like some number like 3, or let's say, for example, if they ask you to graph 3 times V. What does it mean? It means assume 3 times V in general means V plus V plus V. This is what multiplication means, right? You have V 3 times by itself added, so you get 3V. So what it means is you add V to itself 3 times, exactly the same length. What you get is basically rescaled version of the V, right? So this would be rescaled version of. is in the same direction, the length is just multiplied. This number could be 1/2 as well. 1/2 v means just divide the v into half. If this was originally v, you divide it into half. If it is -1 times v, what does that mean? Or sometimes they write just negative v. It means multiply a negative, it changes the direction. The direction would be, instead of going that way, you will have negative. And you may ask, why is that the direction changes? Okay, let me draw it here. So negative v would be exactly this. This is negative. One thing that you should notice is that if you add v with its opposite plus negative v, what you expect is these two must end up to be 0, because you go along v and come back. So here you have v, you come back, negative v. This is one of the reasons that the direction changes. It's just to satisfy this property that there is an opposite direction to the v. If you say negative v, the direction would not be in this way, then it would be an issue to figuring out if there is a 0 for this summation of the vectors or not. So you can draw it this way and say this is negative v, or you can draw it, say here is negative v. It doesn't really matter however you draw it, because it's the length and direction of the vector that matters. It doesn't really matter where you draw it. This is negative v. Okay, so what is u minus v? If you have two vectors, let's say this is u and this is v, what would be u minus v? U minus v, first you have to draw negative v. So this is u. Negative v would be exactly the opposite. If this was v, you can draw negative v here. So what you get is this as u minus v. Okay, it's still the same triangle law, but you have to first draw the negative v, then you draw the u minus v. So far it's just about the graphing. And you notice that I haven't mentioned anything about 2-dimensional, 3-dimensional. So this is general to any dimension. It could be 5th dimension, you still follow the same structure. Okay, here's the difference in the 2 or 3 dimension is the number of components. A vector could be shown based on its component in the form. This is in 2 dimension. It should have 2 components depending on x and y. And in 3 dimension, it has 3 components, like the number of coordinates that you require. So this is in 3 dimension. The vector a in 3 dimension will be shown as a1 and a2. But this is not the parentheses. This is this less than or greater than notation. We use this just to differentiate between vectors and points. If you use parentheses, then there is no it's not clear if you're talking about points or vectors. So for vectors, you use this notation. What is A1? A1 tells you, for example, in 2 dimension. A1 tells you if you start from the origin and try to graph this, you go to the point A1, and then you go to the point A2. So there is the vector A1, A2. You find the point A1 and A2, and from the origin, you draw this vector. This is the vector A into the dimension. In 3 dimension, it would be just a z-axis as well, so you have to draw the vector in 3D. Okay. The only thing is that when you see these components, this is correspond to the point that if you start from the origin. You could have started from here and draw the same vector A here. But the components of this vector would be exactly the same as that. The only difference is you have to say, okay, if I start from a different point, then the terminal and initial would be different. When we write in component form, our assumption is that we always start from the origin to graph. Okay, if you start from somewhere else, if I say, okay, this is the component of vector A, but start graphing it from the point 3 and 2. Then you find 3 and 2 and say, okay, 3 and 2, let me draw the same vector. How do you draw it? You add these components to 3 and 2. If this was 2 and 1, say, okay, this is 3 and 2. Where do I end up if I go 2 right? I'll end up at 5. If I go up 1, I'll end up at 3. So this point would be 5 and 3. So this vector still has the lengths, the format of 2 and 1. Sorry, this is vector. Okay. Normally is in the starting from the origin, unless they say specifically start from a different point and draw this vector. So how do we find the component form of a vector? Is that if you're given 2 points, initial and terminal point, the vector AB is basically can be figured out by finding the lengths along each direction. So the vector AB would be the terminal minus the initial. That is the first component for x, y2 minus y1. Second component, z2 minus z1. Third component of the vector. In 2 dimension, you would have the terminal would be just x1 and y1. The initial and terminal would be x2 and y2. So you find AB in that case to be x2 minus x1 and y2 minus y1. Again, this is not parentheses. So the component, the component of the vector will basically give you these lengths along each direction. Okay, this is the vector AB. Let's do maybe an example before we move on. Sorry about that. Let me pick a better example. Okay, so let's say graph 2 vectors A equals to 2, 1, 0, and B equals to 0, 0, 1. Here, this is a 3-dimensional vector. If you want to graph it, you have to draw the 3 dimension. Vector A would be 2, 1, 0. So here is from here you will go 2, 1 along the y, and 0 along the z. So this is the vector A. Vector B on the other side would be 0, 0, 1. So 0, 0, 1 along the z. This is vector B. If they ask you then to add these 2 vectors, for example, you have to put the B at the end of A and find out what is the vector connecting those 2. Okay, again, drawing would be kind of difficult in 3 dimensions. So I suggest maybe get familiarized with the topic on 2 dimensions, then extend it to 3D. Okay, what do we care about the vector is the direction and the magnitude. Magnitude is basically the length of the vector. So how do we find the length of the vector? And this is something that we talked about in the last section. If you have 2 points, the initial and terminal, how do you find the distance between those 2 points? And we noticed that the distance formula, let me write this again. If you have x1, y1, and z1, and another point x2, y2, and z2, this is points. The distance between these 2 points is basically square root of their differences. x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. Right, this was the distance between 2 points. But look here, what you see is if you have a vector given with 2 points, the initial and terminal, the x2 minus x1 is basically the first component of that vector. y2 minus y1 is the second component of that vector. And z2 minus z1 is the third component. So basically, to find the length of a vector, what you need to add is the components square. Add the components square and take a square root. So if you want to find the magnitude or the length of a vector with the components v1, v2, and v3, basically square the components, add them up. This is from the distance formula that if you wouldn't have talked about it in the last section, now we couldn't have calculated this. And one important thing is that the absolute value of v means the magnitude, as well as if you have these double lines, double parallel lines, sometimes called norm, the norm of the v or the magnitude of v. They both used often, so know both of them that represent the length. So here, for example, if you have the vector, let's answer these questions. If you have the vector a as 2, 1, 0 and b as 3, 0, negative 4, if they ask you to find the magnitude of vector b, it would be to take a square root of the sum of the components, 3 squared plus 0 squared plus negative 4 squared. It would be 9 plus this would be 5. That means this vector in 3 dimension, when you graph it, has the length 5. The length of the vector, the distance between these 2 points, would be simply 5. What is 2a minus b? 2a minus b, we haven't talked about the addition and subtraction yet. We have it in the next section, but I just wanted to say that if you don't know the addition and subtraction by calculation at the moment, what you can do is first you can draw it, then figure out what is 2a minus b. Okay, so let me ignore the b for the moment. If they ask you to find out what is 2a, what does that mean? That means draw a. Okay, let me mention it in 2 dimensions, then we go into 3. This is a, for example. 2a means the same vector added to itself. So if the components are at a1 and a2, what do you expect is that another a1 added and another a2 added here. So you will get 2a2 and 2a1. So what is the component of the new vector? Is basically rescaled. So 2a would be 2 times each entry. It would be 4, 2, and 0. This would be the vector 2a. So on the other side, what would be negative b? Negative b would be negative 3, 0, and positive 4. Okay. If they ask you what is the length of the negative b, without calculation, you should be able to answer this. Because multiplying a negative doesn't change anything about the length, it just changes the direction. So what is the length? It's still supposed to be 5. Right? But if you multiply a constant like 2, you rescale the vector. So if the vector has length, for example, 5, and if you multiply 2, the new length would be 10 for the vector. So if we would have found the magnitude of a, if I would have asked magnitude of a would be square root of 2 squared plus 1 squared plus 0 squared, which would be square root of 5. So what is the magnitude of 2a? If you calculate, you get 4 squared plus 2 squared plus 0 squared. If you simplify this, this is square root of 16 plus 4, which is 20. You can write this as 2 square root of 5. What you notice is exactly that this is twice as the norm of a. So multiplying, rescaling a vector, it just rescales the length. The direction doesn't change, it just rescales the length. So if you know the lengths of the vectors already, you can answer these certain questions about the rescaling. On the other side, if you add them together, if you add 2 vectors, then it would not hold it. The lengths would be added to each other. For example, if you have vector a added to vector b, the length of a plus the length of b is not the same as the length of this line connecting these two. If this is a plus b, these magnitudes, they cannot be added to equal each other. Magnitude A plus magnitude B does not equal to magnitude A plus B. Don't make this mistake. You have to calculate this. But first, let's figure out how to calculate the addition. So here are some of the properties of vectors A and B and a constant C. So let's assume we have a constant C. If you add a vector A and B, doesn't really matter in what order you add them together. You still get the same result. So if you have A and add it to B, it's the same as saying I write B first, then add it to A. You will still end up with the same A plus B. This is A plus B or B plus A. They are the same thing. So rearranging the order of addition doesn't make any difference. And the same, if you add three vectors, doesn't really matter how you add them, you will still get the same result. If you add a zero, this is not a zero as constant, this is a zero vector. That means there is no movement, it's just the endpoint. If you add a zero vector to a vector A, you still get a vector A. This is vectors. If you have a vector A with its opposite vector, you're getting zero. That's how we define the opposite vector. And if you multiply a constant, C here is a number, to sum of two vectors, you can distribute. You can say C times A, C times B. That's not an issue. You can rescale the vectors first and you add. And 1 times a vector A is still a vector A. It doesn't do anything. It's an identity. It doesn't rescale or shrink the vector in any way. Okay, so here are some standard basic vectors. Then we will do examples. Okay, standard basic vectors. Certain vectors that we care about is the ijk vector. What are the ij vectors? Ijk. They're specifically defined to be along the axes. So for example, in 3-dimension, this is first in 3-dimension. You have three components. 3-dimension, the I vector is along the x with the length of 1. This is the I vector. Length 1. It's 1 for x, 0 for both. J vector is along the y with the length 1, and z vector is along z, k vector is along z with the length of 1. In 2-dimension is the same thing. Length 1 is I and j. It's not the imaginary number I. This is a vector, standard vector. We pick these names already as ij. Sorry about that. Okay, so this is the basic standard vectors. You can write the components of a vector based on this standard vectors. Here we do an example just to see how it looks like. Okay, so let's say you have two vectors A and B. First, figure out what does A and B look like. A says negative 2i, j minus 2i plus 3k. So j minus 2i plus 3k. This is in 3-dimension. I should have mentioned 3-dimension. Okay, so it means you have the j vector, which is, let me write A. A is, j is 0, 1, 0, minus 2 times I is 1, 0, 0, plus 3 times k is 0, 0, 1. But we learned that if you multiply, a constant to a vector, you just need to multiply that constant to every component because you're rescaling the vector. So what we get here is for A would be 0, 1, 0 minus 2 times 1. You can multiply the negative inside as well if you want. You can write this plus negative. So you would have plus negative 2 multiplied by 1 would be negative 2, 0, 0. And plus 3 times that would be 0, 0, 3. There's a faster way to do this, but I want you to see generally. How you add the components of the vector. If you add the components of the vector, you add them correspond to each other. So you add all the x's together, all the y components together, and so on. So what we get is 0 plus negative 2 plus 0, you'll get negative 2. 1 plus 0 plus 0, you'll get 1. And 0 plus 0 plus 3, you'll get 3. So what we have for vector A is 2, 1, and negative 3. So vector A would be negative 2, 1, and 3. You didn't need to go through all this just to find vector A, because they already tell you what are these coefficients. Here coefficient is 1, coefficient is 3. The coefficient tells you the component. I was correspond to x, so here is negative 2. J is correspond to y, so here is 1. And k is correspond to z, so here is the component of that. So this, if you use the standard form, it already tell you the components of the vector. So for example, now what is b in component form? I is coefficient 1. J, there is no j, so 0j. And k has coefficient 1, so here's k. So what would be a plus b? There are two ways. You can already add a and b through components, or you can add them through the standard form. Let's do both ways. So let's do the standard form. So you would have j minus 2i plus 3k plus I plus k. So how do we add these two? You add the corresponding I and j together. So I, you will have negative 2i and 1i, you'll get negative I. There is no j plus j, and 3k plus k, 4k. So this is the standard form of adding a and b, if you're using the standard vectors. If you use the component form, what you get is negative 2 plus 1. I'm adding these two together just to double check. Negative 2 plus 1, you get negative 1. 1 plus 0, you'll get 1. And 3 plus 1, you'll get 3. Sorry, 4. So compare these two. Coefficient negative 1, coefficient 1, coefficient 4. Exactly the same thing. You can find the vector A and B added together. Whichever looks easier to you, you can use that. How do we find the magnitude of A? You can find the component form first. Then you can square the components and add them together. You can write square root of negative 2 squared plus 1 squared plus 3 squared. Whatever that is. This is 4, 5, and 9 square root of 14. Or you can look at the coefficient again. Here 1, negative 2, and 3. So I'll write 1 squared plus negative 2 squared plus 3 squared. It's the same thing. Square root of 14. It doesn't require you to write this in a component form, then add them together. The only thing that you should make sure that is there is one j, not two of them. So for example, if they write a equals j minus 3j plus 4, okay, you cannot say, okay, this is 1, negative 3, and 4. This is not correct because they're both j, so you have to first simplify this and say, okay, this is negative 2j. So I would have negative 2 here, and there is no I, 0. This would be the corresponding vector A. This is the important part of it. Okay. So this is a good example. You can try to write example for yourself. Try to work out in 2 dimensions. I did for 3 dimension. If you know 3D, then 2D would be easy. Okay. One last thing that we need to mention is the unit vector. What is a unit vector? Definition of a unit vector is in its name. Unit vector, which means it has the length of 1. That's the only restriction. For example, I, J, K, they were unit vectors. They all had length 1. But those are not the only vectors with length 1. So in 2 dimensions, for example, you could have a vector. Here, I has length 1, as well as this could be this vector with the length 1. That's a unit vector. It could be this length 1. So anything along the circle, our radius 1, any vector, that would be a unit vector. That's why we had sine and cosine in trigonometry, because all these points along the unit vector, along the unit circle, are basically depending on the cosine and sine values. So because if you know the cosine value here, this was cosine theta and sine theta. So if you know the angle theta, then you know the unit vector, which is cosine theta plus sine theta, plus, normally they write it as cosine theta I plus sine theta j. The two standard vectors. With 3D, you can extend the same idea. We'll talk about it later, but first let's understand what is the unit vector and how do we find the unit vector for the same direction as we want. So if you have a vector A, let's say given vector A, which doesn't have length 1, if this is vector A, and they ask you to find the unit vector u along the same direction of A. So if I want to find the vector along the same direction with length 1, u, the only thing that I care about is just to rescale A somehow to be a length 1. So if I want to find vector u, I have the same vector A, I just need to rescale it to be length 1. That means I need to divide it by its length. So I can write this as A divided by its length. This way I get a vector that has length 1, because its own length divided by itself, the vector itself by divided by its length would be 1 simply in terms of length. Sometimes they write it this way, times A. For example here, A is 2i minus j minus 2k. If you were looking for the unit vector, so they say find the unit vector along A. Find u, unit vector, u, in direction of A. So what we need to do is first find the magnitude of A. It will be square root of 2 squared minus 1 squared, plus negative 1 squared plus negative 2 squared. What you get is 4, 8, and 9, so this is simply 3. So what would be the unit vector? The unit vector would be 1 over 3, 1 divided by the magnitude of A, multiplied by the vector A, which is 2i minus j minus 2k. Let me use parentheses. So 1/3 times that would be 2/3 I minus 1/3 j minus 2/3 k. Just to make sure that you have the unit vector, you can double check and calculate the magnitude of this vector u. Figure out what is the magnitude of this vector u. Do the same components square, add them up together to see if you get 1. If you don't get 1, then there is a mistake, but I can see that this sums up to simply 1. Okay, so this is the unit vector. We will see more of application of this later on, but at the moment it's just to discuss how does a unit vector look like in the same direction of a vector. There are some applications of the vectors. There's one that I wrote here. Maybe in the homeworks you will see more. So here, let's do this one. What is the application? Normally in physics you'll write forces in terms of vectors. So let's say there are 2 wires. This is a ceiling, for example, here. And the 2 wires are attached to a weight of 100 pounds. And these wires hold this weight. And there is forces along each direction. Let's call it T1 and T2 along the wires 1 and 2. And we want to figure out what is the amount of forces for each direction. And what you notice is always there are certain angles given here, 60 and 30 degrees. What you notice always is that you have to always break this down along to the x and y axes, because we have 2 dimension, not 3 dimension, so there is no need to go to 3D. And the important thing to notice is sum of all three whatever the result is, since this is in a balance and it's not moving, the sum of everything must be 0. So it means there is no force that is pulling. If they would say that this is moving along that direction, it continues to move, then there will be certain force still would be putting on these wires. So on the other side of the equality, if you're creating any equality, you would have not equal, you would have equal to that force. So here, first let's look at the vector t1 and t2. We want to figure out what are the vectors. So I drew this picture into x and y plane. So here is the x, here is the y. Okay, one thing to mention is if you draw the x and y here, it's easier to see it, maybe. But you can answer this question, what is this angle? This angle is 60 plus 90 plus something here. This must be 30, which means this is 60. Or you can say these two are parallel, so therefore that is 60, this must be 60. So I can say that this angle here is 60 degree. Similarly, that angle must be 30 degree. And the 100-pound weight is along the y-axis downward. And here is what I mentioned earlier. The sum of all forces must be 0, because this is in a balanced situation, it's not moving. So what I'm going to do is I'm going to try to break down these vectors. This is a vector v, t1 and t2, and write them in a component form. How do we do that? Figure out what is this component, figure out what is that component. The same as here. We need to figure out the components of each vector. You're given the angle. Now this is where the trigonometry comes in. If we know the lengths, so this is the length of t2, and here we have the length of t1. This length here would be the length of t2 multiplied by the cosine of this angle, because cosine of the angle would be correspond to the x value. So this would be, if that would have, let's say you want to find out star, let me call this length star. What would be cosine of 30? Cosine of 30. If you look at the triangle that we have here, it would be the adjacent divided by hypotenuse. It would be star divided by the length of t2. Right, so the cosine of 30 would be that. Which means if I'm looking for star, it would be this guy multiplied by cosine of 30. So I can figure out this length and say this is t2 multiplied by the cosine of 30 degree. If it was theta, you would have put theta, but we already know the angle. And here the same. On the other side, what we have is t1 multiplied by cosine of 60. The only thing that you should notice is that this is in the negative area, so I'm going to put the negative sign there. And you would have t1 multiplied by sine here. This height would be magnitude of t1. Here, this would be magnitude of t1 multiplied by the sine of 60. And the other component of the vector t2 would be the length of t2, magnitude of t2 times sine of 30. They all come back to this structure. The sine and cosine correspond to the x and y coordinate on the unit circle, which means you really scale it based on the triangle. So I can write the vector t1. This is the vector t1 in terms of their components. So t1 would be negative magnitude of t1 times cosine 60 degree I, that means along the unit vector I, along the x-axis, and here you would have t1 magnitude times sine of 60 degree. And same would be T2 times cosine 30 degree plus T2 times sine 30 degree. Okay, we know sine and cosine values, so I'm gonna write those as well. Simplified version maybe. So T1 would be magnitude of T1, negative, there was a negative there. Here, negative T1. Cosine 60, cosine of 60 would be 1/2. So it would be times 1/2. Let me put them in order. So minus 1/2 magnitude of T1, I, plus square root of 3/2 is the sine value, magnitude of T1. You can factor out the magnitude of T1 if you want, J. And T2 would be it's exactly the same thing. Instead of cosine 30, you will get root 3/2. Instead of sine 30, you will get 1/2. So you get root 3/2 magnitude of T2 I plus 1/2 T2 J. Okay, I and J are the corresponding standard vectors. And what is the other vector? The other vector, we already know. It's 100 along the negative J. So our third vector, maybe I should call it, let's call this vector V. This is vector V, maybe W for the weight. It's negative 100 along J. And so what we know is the sum of all these three must be 0. That's what we know. That's what we expect from the wires to hold this weight. So the tension created by these three would be the sum of all these three must be 0. I can write this as negative 1/2 magnitude of T1 I plus square root of 3/2 magnitude of T1 J plus root 3/2 magnitude of T2 I plus 1/2 magnitude of T2 J minus 100 J must equal to 0. This is what we get from adding these two. So what we can do is now we can combine the like terms. This term has I as well as this term. Everything else have the J. So I can say these two, negative 1/2 magnitude of T1 plus root 3/2 magnitude of T2 I, they all have I, plus the other term is root 3/2 magnitude of T1 plus 1/2 magnitude of T2 minus 100 J equal to 0. Okay, so this becomes 0 only if both of these components are 0. This is the only way that we have 0, because I and J are in different direction. They cannot be combined together. So what I can create is to say this is 0 or this is 0. So what we get is from the first one, you'll say these two added up together must be 0. So what I can get is negative 1/2 magnitude of T1 plus root 3/2 magnitude of T2 equal to 0, which means I can get some equation out of this. You can multiply both sides by 2 and move this one to the other side, so you'll get magnitude of T1 simply equals to root 3 magnitude of T2. This is what we get from the first equation. You can multiply it to get rid of these two denominators and then move that to the other side. So this is the first equation that we can get. And now into this part, instead of magnitude of T1, I can replace root 3 magnitude of T2. So what do I get is, here I'll replace root 3 over 2 times, instead of magnitude of T1, you can replace root 3 magnitude of T2 plus 1/2 magnitude of T2 minus 100 equals to 0. So this is 3/2 plus another 1/2. So 3/2 and 1/2 would be 4/2 divided. So that is 2 magnitude of T2 equals 100. And so I can answer this question. What is the magnitude of T2? It is 100 divided by 2, or 50. And what is the magnitude of T1? Simply, we found out the magnitude of T2, so it would be root 3 times 50. Or you can write it as 50 square root of 3. And we answered the question. What is the forces along each direction? We found the magnitude for each direction. Okay, so this was an application. It's a bit too long to calculate, but it's not difficult. The only important part is that you can find the components of these vectors. This is where you need the trigonometry that you learned in Calc 1. If you don't remember it, just go back a bit to review those. Okay, I'm going to stop here, and next time we'll continue on section 3.